All right, let's talk about waves. You know, the basic sine and cosine curves, they're nice, they're predictable, but what if we could grab the controls and start shaping them ourselves? Make them taller, or faster, or just different? Well, that's exactly what we're diving into today.
So here's the big question, right? How do we take something simple like y equals sine of x and just play with it? How can we stretch it out, squeeze it together, and really customize it?
You know, the whole thing really boils down to this super simple idea. Think of it like a sound wave. We can either make it louder or we can make it faster. Seriously, if you can get your head around those two things, you're pretty much set.
Okay, let's tackle loudness first. In math speak, we call this the amplitude. It's really just a word for how we stretch the wave up and down, vertically. So what is amplitude? It's just the height of the wave. Well, to be precise, it's the distance from the middle line all the way up to its highest point, or peak. And here's the key. If you've got an equation like y equals a times sine of bx, the amplitude is just the absolute value of that number a out in front. And think about it. It's a distance, right? So it can't be negative, ever. That's super important to remember.
Let's see this in action. We start with our good old y equals sine of x. Its amplitude is 1. Now watch what happens. If we change that a to a 2, boom, the wave is suddenly twice as tall. We've cranked up the loudness. Now what if we change a to, say, zero point 0.5? The whole thing gets squished down to half its height. See? That a value is like a volume knob for the wave. All right, we've got the loudness down. Now for the speed. This is all about the period of the wave, which is how we control that horizontal squeeze and stretch. Okay, so the period is basically the wavelength. It's the horizontal distance it takes for the wave to complete one full cycle, from peak to peak. But here's the big gotcha, and you really got to pay attention to the formula here. You don't just find the period in the equation. You have to calculate it using that b value. It's always going to be 2 pi divided by the absolute value of b. And this right here, this is probably the biggest mistake people make. So let's really nail this down. B is not the period. Think of B as the frequency. It tells you how many full waves are crammed into that standard 2 pi space. So if you think about it, it makes total sense. The more waves you squeeze in, a bigger B, the shorter each individual wave has to be, right? So they have an inverse relationship.
So let's watch it happen. Your standard sine wave takes a full 2 pi to do its thing. But look what happens when we change the equation to sine of 2x. Suddenly, the wave is moving twice as fast. You can literally fit 2 complete cycles into the same space where we used to only have 1. And hey, look at that. Our formula works perfectly. The period gets cut in half, from 2 pi down to just pi.
Okay, enough theory. Let's get our hands dirty and actually use this stuff. We're going to run through some examples to see how these two pieces, amplitude and period, work together. All right, check this one out. Y equals -3 times cosine of 4x. Let's break it down. First up, amplitude. I see that a value is -3. But wait, amplitude is a distance, it's always positive. So we take the absolute value, and our amplitude is just 3. Simple. Now for the period. The b value here is 4. That means this wave is 4 times faster than normal. So we plug it into the formula, 2 pi divided by 4, which simplifies down to pi over 2. That's it. 2 easy steps. Okay, let's switch it up, this time or working backwards. We want to build a sine wave that has an amplitude of 2 and a period of 6 pi. Well, the amplitude part is a piece of cake. That's just our a, so a equals 2. But for the period, we have to do a little work to find b. We just use our formula. We know period equals 2 pi over b. So we plug in what we know. 6 pi equals 2 pi over b. Do a little bit of algebra, and voila! B has to be 1/3. Now we just put the pieces together. Y equals 2 times sine of 1/3 x. Now for the final boss. Pull in an equation right out of a graph. First things first, amplitude. Just look at the graph. The highest point it reaches is 3, so our a value is 3. Done. Next, the period. Let's trace one full cycle. See how it starts at 0 and finishes its whole journey at pi? That means the period is pi. Now we can use that to find b. We set up our formula. Pi equals 2 pi over b. And if you solve that, you get b equals 2. So we just assemble our equation. Y equals 3 sine of 2x. Not so bad, right? Okay, we've done a bunch of right answers, but now let's talk about the 2 most common traps I see people fall into. If you can avoid these, you're golden. First one is this. You see an equation, something like y equals -5 sine of x.
And the question is, can the amplitude be negative?
And the answer is a huge flashing no. Never. Amplitude is a distance, remember? It has to be positive. So what's that negative sign doing out front then? All it does is reflect the graph. It flips the whole thing over the x-axis. So instead of going up first, a sine wave with a negative in front will go down first. The height, the amplitude, is still a positive 5. The negative is just a flip.
And here's the other big one. We talked about this, but it's worth saying again. You see that b value tucked inside the parentheses. Is that number the period, plain and simple?
No. Nope, nope, nope. This is the #1 trap. Please don't fall into it. B is the frequency. It's not the period. You must always use the formula. Period equals 2 pi divided by b. If you see sine of 4x, the period is not 4. It's 2 pi over 4, which is pi over 2. They're totally different ideas. You've got to do the calculation every single time.
So let's just boil it all down into one simple table. This is your cheat sheet right here. A controls the vertical part, the loudness, and its absolute value is the amplitude. B controls the horizontal part, the speed, and you use it in the formula, 2 pi over b, to find the period. If you can remember this, you've basically got it all.
Okay, so I want to leave you with one last thing to chew on. We know that a bigger b value makes the wave faster, more scrunched up. So think about it. As you make these waves faster and faster, what do you think that does to the steepness of the wave at any given spot? It's a cool question, and it's actually hinting at some really powerful stuff you'll see down the road.